Greetings, everybody. We're doing this week's SDQA, getting ready for our midterm exam. With that in mind, I want to give you a sneak peek at something that looks very similar to a part 2 question on your exam coming up. And what we have here is we have part 2 Lewis structures and redox. Yours will look exactly like this with the boxes in the same places and these blanks in the same places. The molecules will change. That's it. And what we have here is a small alkene propene, which you're going to have to draw the Lewis structure of. Yep, it's going to be species 1. You draw the Lewis structure right here in a box. And species 3, you're going to draw the Lewis structure of this in this box. You're going to give the oxidation states in these boxes for these atoms C and D and E and F and G and H. And the point counts are, it's going to be 14 points. 2, 4, 8, and 6 is 14 more points. Let's get started. Lewis structure has to show all the valence electrons. So we need to get the carbon skeleton here, C, C, C with a double bond there, H's on the end. There's 2 of them, CH2, H on the middle carbon, 1 of them, 3 H's on the last carbon. Make sure you show all those bonds. Lewis structure has to show every bond and every lone pair. Remember that. Species 3, every bond, every lone pair. This parenthesis here means the OH is attached to the previous carbon. So we do have the same skeleton with 1, 2, 3 carbons in a row. CH3 on the end did not change. The next C over still has 1 H, but it now has a new OH. Don't forget, oxygen needs to have 2 lone pairs. And the next carbon over has 2 H's still, but it has a new OH as well. So we added a new OH to each carbon that used to be part of an alkene. Alkene became alcohols on each carbon. Just to keep it straight here, we're going to be doing our answers based on our Lewis structures. That's C and D, and this is F and G. Okay. So what I'm going to do, I'm going to do oxidation states next. And I know you can't do this on your test, but I just want to show you, there's the Lewis pictures. I'll do oxidation state rough work over here. You could do this on a piece of scrap paper. This is for oxidation states now, so there you go. When you do the oxidation state of atom C, you have to look at every bond to atom C. You have 3 choices for a number for every bond. 0 if you're bonded to the atom, an atom with the same electronegativity. -1 if you're bonded to an atom with a lower electronegativity, such as hydrogen. So my oxidation states are going to be in green. We get a -1 for a bond to H, and the hydrogen gets a +1 for a bond to the more electronegative carbon. Carbon bonded to a carbon gets a 0. And each side gets a 0. Same here for this sigma bond, and same here for this pi. So for the carbon, add up the 4 numbers. You got 3 zeros and a -1. So for C, you're going to put -1. Same carbon as F. When you're done, let's look at it. You get a -1. You get a 0. You get a 0. And because oxygen's more electronegative than carbon, carbon gets a +1 for that. Add up all these numbers and you are looking at a 0. That carbon underwent a oxidation. How do I know that? I don't want this air running into my blank there. That carbon going from C to F underwent oxidation. So that atom became oxidized, C. Here's your choices for I. Choices for 1I and J are C, D, and E. Okay, so I just put a C. You don't have to write the 1. Okay, let's look at atom D. You get a -1 for each of the bonds to H. You get a 0 for the bond to carbon, which we already have on there. So the 4 numbers are -1, -1, 0, 0. Add them all up, you get -2. We'll put that in a different color. Okay. And D went from -2 to being G. So you get a -1 there and a -1 there and a positive because it's bonded to an oxygen and a 0 there. You get 2 negatives and a positive. That's -1 and a 0, still -1. Okay. Going from -2 to -1. Also oxidation. You know how I know? The number went up. I don't think I said that before. The number went up. Oxidation state means your oxidation means your oxidation state gets higher. And so that means atom D also became oxidized. Yes, we can have more than one atom becoming oxidized. All right, where is, let's see, we haven't done atoms, let's see, we've done 4. We have to do E and H, which are both osmium. Now, if you really like the Lewis structure method and doing all the bonds, that's great. Love it. You've bought into the new and improved version of doing redox. You can still, for an inorganic molecule like this, do the old school mathematical determination of oxidation state. So for 1E, you've got X for osmium plus -2 times 4 equals the charge on the species. And do you have a charge on the species? The answer is no, which means the charge on the species is 0. It's neutral. So X equals a whopping -8. You do not hardly ever see such -8, +8. If I put -8 there, -8 plus -8 is -16. That's not 0. 8 plus -8 is 0. So it's a whopping +8. Same story for H. Remember, hydrogens have an oxidation state in normal molecules of +1. There's 2 of them. We're solving for a new X. And each oxygen's -2. Normal oxygens anyway. And you get that. And you solve that, you get X equals +6. That's a lame attempt at a plus sign there. All right, 2 plus 6 is 8. Wait a minute, is that right? I don't even think it's +6, is it? No. Bad math. Bad math. I think it's 4. 2 plus 4 gives +6, and -6 gives 0. Hello. 4. So E going to H, it's going down. That's a reduction reaction. And it went down. So that is atom E becoming reduced. Which atom became reduced? E. Okay, these two questions are simple, but you do have to know this wording. There's only one definition of reducing agent. Forget the thing you put in your memory bank that says a reducing agent becomes oxidized. That's not the definition of reducing agent. You'll see that lame discussion in all my videos. Reducing agents cause the other molecule to become reduced. That's the only definition. In so doing, they become an atom in there becomes oxidized. Yes, the consequence, it's not a definition. All you have to do is identify which atom got reduced and label the other molecule as the one that caused it. The atom that got reduced was E. This thing got reduced by the other molecule. Species 1 is the reducing agent. Let's put a 1 there. It says choices for 1K and 1L are species 1 or 2. I don't need the word species, put the 1. Okay, identify which atoms became oxidized. Well, both carbon C and carbon E, C and E, wait, did I do this right? No. D, there, D, sorry. D became oxidized, C became oxidized, and they're both in the same molecule. That oxidation was caused by the other species, which is species 2. Easy points there. Did we get all of our points? I think we did. I'm gonna finish up by doing the +8 and the +4 using the Lewis method. The Lewis method is foolproof with no memorization of exceptions. OSO4 looks like this. Remember, oxygen's nature is to have 2 bonds, 2 lone pairs. So this would be atom E. Each bond to oxygen gives an oxidation state of +1. There are 8 of them. 8 times +1 is +8. Species H, sorry, whatever this thing is, it wasn't labeled. It's an oxy acid. Don't know what that means? Find it in chapter 1, where near the end of the Lewis section, Lewis structure section, it talks about oxy acids, which means the H is bonded to the O and not the other atom, which is OS, osmium. So when you're finished with this one, its Lewis structure looks like this. Oh, I have an extra O. I have an extra O. Don't do that. There's 3 O's. I'm determined to make the same mistake consistently of giving this an oxidation state of +6 instead of +4. Right now it's +5, isn't it? H2SO3. Yeah, I hate to admit it, but there's a mistake in this problem. I don't have 2 H's on there, do I? Yeah, if there's going to be 2 H's, they're both on the O's. I finally think I have the +4. And in retrospect, I think this method was a little faster. Sometimes the old school method's faster. Each bond to O gives a +1 oxidation state for osmium because O is more electronegative. You don't need to know the electronegativity of osmium. If an atom that's a metal is bonded to oxygen, the metal is always less electronegative than oxygen. So +1, +1, +1, +1, 4 times. There's your +1. And that brings to a conclusion this segment. What's going to happen now is I'm going to stop this. I'm going to come back in about 10 minutes, maybe 5 minutes. And if anybody is there, then we will do a segment of your choosing and request. If not, then this day is over, and you need to continue studying, because I know you're all studying very rigorously. And we'll see you in 5 minutes, or not if you're not there. Adios.